All right, today we're going to pull back the curtain on one of the most important concepts for making things fast, caching. Seriously, it's the secret ingredient behind almost every high-performance system you use. And trust me, by the end of this, you're going to see it everywhere. So, let's just dive right in.
So, you ever wonder about this? Why are some websites and apps just blazing fast, while others, well, they just feel sluggish? You're sitting there, staring at a loading spinner, and it's just a universal frustration, right? The reason for that difference, more often than not, boils down to one really powerful idea.
And yep, you guessed it, that secret ingredient is caching. It's this really elegant concept, and once it clicks for you, you'll start noticing it in everything from your web browser all the way up to the massive architecture of global services.
Okay, so here's our game plan for today. First, we're going to start with the absolute basics. What even is caching? Then we'll get into the rules of the game, cache policies. We'll look at two of the most famous ones, LRU and LFU. After that, we'll tackle some more advanced patterns and finish up by looking at the big picture.
All right, let's kick things off with part one, what is caching? We're going to break down the simple idea that's behind speeding pretty much everything up.
You know, the best way to get this is with a super simple analogy. Imagine your cousin comes up to you and asks a tough multiplication question, like, hey, what's 58 times 32? You figure it out, do the math. Then, like an hour later, they ask you the exact same question again. Are you going to do all that math over? No way. You just remember the answer you already figured out. That act of remembering, that's a cache. Your brain just acted as one.
And that's pretty much the technical definition right there. A cache is just a smaller, much faster place to store copies of data you use a lot. It's all about avoiding the pain of going back to the original source, the slow part, over and over again.
So why bother with all this? Well, there are a few huge wins. First, you get to avoid slow network calls. Think about fetching a user's profile from a database across the network versus grabbing it from memory right next to the app. It's a no-brainer. Second, you get to skip expensive computations. Let's say you need to calculate the average age of all your users. You don't want to do that every single time someone asks. You do it once and you cache that result. And both of these things lead to the big one. You seriously reduce the load on your main database, which is almost always the bottleneck in any big system.
Okay, so this all sounds amazing, right? But it leads us to the biggest challenge with caching. A cache is, by design, small. So, what happens when it gets full? You need some rules. You need a way to decide what to keep and what to throw away. And that's where cache policies come in.
See, the whole reason caches are so fast is because they run on really expensive hardware, like RAM. And that stuff is way more expensive than your standard disk storage. So because of that cost, we just can't afford to make them huge. We can't store everything. It's a fundamental constraint.
And that creates this really interesting problem, right? The cache is full, a new piece of data needs to come in, something has to get kicked out. So how do you decide? How do you make the best guess about which piece of data is the most evictable, the one you're least likely to need again anytime soon?
Well, the answer to that question is something called a cache policy, or sometimes you'll hear it called an eviction policy. It's basically the algorithm, the set of rules that the cache uses to make that decision. And honestly, picking the right one can make or break the performance of your entire system.
So let's get into it. We're going to look at two of the most popular strategies out there, the ones you'll hear about all the time, especially in system design interviews. They are the true workhorses of caching, LRU and LFU.
Okay, so first up is LRU, which stands for Least Recently Used. The logic here is pretty simple. If you haven't touched an item in a long time, you're probably not going to need it again soon. So it finds the thing that's been sitting there the longest and boots it out. Then you've got LFU, or Least Frequently Used. This one works on a different bet. It says, hey, how popular is this item? It keeps track of how many times you've accessed something and kicks out the one that's been used the fewest number of times.
Let's walk through an example of LRU to make this super clear. Imagine our cache can only hold three things. So step one, we put in item 1. Easy. Cache has 1A. Step 2, we put in item 2. Now 2 is the most recent, so it goes to the front. You see, the list is ordered by recency. We do it again with item 3, and it goes to the front. Now here's the important part. In step 4, we access item 2. Watch this. Because we just used it, it jumps all the way to the front of the line. It's now the most recently used. Finally, step 5, the cache is full, and we need to add item 4. What does LRU do? It looks at the very end of the list, the least recently used item, which is poor old item 1, and that's the one that gets evicted.
Okay, now let's do the same for LFU. This time, our cache capacity is just 2. We put in item 1 and item 2, and you can see we're tracking their frequency, which starts at 1 for both. Now in step 3, we access item 1. This is the key. Its frequency count gets bumped up to 2, while item 2 is still sitting there at 1. And here's the moment of truth in step 4. We need to add item 3, but we're full. LFU doesn't care about what was used last. It looks at the frequency counts. Item 1 has a count of 2. Item 2 only has a count of 1. So item 2, the least frequently used, is the one that gets the boot. And of course, if we try to get item 2 after that, nope, it's gone.
Okay, so now we know how a cache decides what to kick out. But that's only half the story. The other half is, how does our application actually interact with the cache? How does it read and write data? This gets into some really cool architectural patterns.
So let's break down these 4 common patterns. The most common one you'll see is called cache aside. Think of this as the do-it-yourself approach. Your app asks the cache, hey, do you have this? If the cache says no, that's a cache miss. Then your app has to go get it from the database itself and then put it in the cache for next time. Now compare that to read-through. This one is a bit fancier. Your app just talks to the cache, period. If the cache doesn't have the data, the cache itself is smart enough to go fetch it from the database. It makes your app code a lot cleaner. Okay, now let's talk about writing data. With write-through, your app writes to the cache, and the cache immediately turns around and writes that same data to the database. It doesn't tell your app I'm done until the database is updated. Super safe, great for consistency, but a little slower. And the polar opposite of that is write back. Your app writes to the cache, gets an immediate OK, and moves on. The cache then saves that data to the database later, in the background. This is crazy fast for the user, but you see the risk, right? If that cache goes down before it saves to the database, poof, that data could be lost.
All right, last section. Let's zoom out and look at the big picture. We've got our eviction policies, we've got our read/write patterns, but there are 2 last really important questions. First, where do we actually put the cache in our system? And second, how do we handle the huge problem of data consistency?
So, where should the cache live? This is a huge architectural choice. Do you put it right there inside your application server? Or do you make it a totally separate thing that everyone talks to? Both have some major pros and cons.
This really boils down to a classic trade-off. Option 1, an in-memory cache. It lives right there on your app server. The pro, it's ridiculously fast. There's no network involved. The con, if that server crashes, all that cache data is gone, and if you have multiple servers, they all have their own separate, inconsistent caches. Option 2, a distributed cache, like Redis. This is a separate service that all your app servers talk to. It's way more resilient. If one app server goes down, the cache is fine. But now every single cache request has to go over the network, which is always going to be slower.
And this leads us to maybe the single hardest problem in all of computer science: caching and consistency. As Gaurav Sen says here, what happens when the real data in the database changes, but your cache still has the old version? That's a huge issue. If you mess this up, you're going to be showing your users stale, incorrect data.
So how do we deal with that? Well, a lot of it comes back to those write patterns we talked about. Remember write-through? By writing to the database immediately, it keeps things highly consistent. This is what you'd use for the really important stuff, right? Like financial info, passwords, things that have to be correct. But then you have write back, which is all about performance. It's okay if things are a little stale for a bit. Think about the number of comments on a post. If it's a few seconds out of date, who cares? So there's no one right answer. It always depends on what your application needs.
So if there's one thing to take away from all this, is that there is no best caching strategy. It's an incredibly powerful tool, for sure, but every single decision you make is a trade-off. Are you optimizing for speed or for cost, for raw performance or for data consistency? You're always playing that balancing act.
So I'll leave you with a final thought to chew on. Now you have the building blocks. Imagine you're tasked with designing the caching system for something like the X-Feed. You've got millions of users, data is changing every second. What would you do? Which eviction policies would you use? Which write patterns? It's a really fun problem to think about. Thanks so much for joining me.